Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is You Ask, We Answer, a panel discussion on relay testing and maintenance. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the technical moderator for today's presentation and supporting you on any technical issues or questions for our panel. Also in attendance in the background as technical support is David Beard, Relay Applications Engineer, and Daniel Carreño, Applications Engineer. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time in the box highlighted in red, and I will integrate them into our discussion here today. Additionally, a certificate of attendance, copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our host today is Eric Titus, Deputy Director of Southeast Region and Strategic Accounts. I will be sending that over to him shortly, but briefly, we're going to touch down on the structure of our seminar today. In our You Ask, We Answer panel sessions, we will have the questions submitted to us from our attendees and registrants, answered in the order they were received and importance. Our panel today is composed of experts from Megger and other companies who have gathered here today to answer and comment about the different questions and topics from the audience. Our panel of selection today is composed, as stated before, of Megger employees and a number of distinguished engineers, such as Schweitzer Engineering and Power Grid Engineering. All this information, including contact information and PowerPoint, will be disseminated to our attendee group shortly after the webinar. With that, I will hand things back over to our host today, Eric Titus. Eric, thank you so much for joining us today.
Thank you, Michael. Welcome, panelists, and welcome, audience, for taking time to join us for this relay panel. And we've got several questions, and nothing like jumping right in. First, we're going to cover some topics. First one being introduction to protection and testing. And the first question I have is actually for VJ. How does a relay operate?
That's a good question. Thank you, Eric. Welcome, everybody. My name is VJ. I work for Power Grid Engineering. For the question, how does a relay operate? Basically, the voltage and current amplitudes are being monitored by the CTs and PTs in your system that are embedded in the transformers and breakers. So they monitor the amplitude, phase, and frequency. Those are the 3 measured quantities. They constantly measure it and send it to the relays. The relay have a set value, and beyond the value or underneath the threshold value, if the measured value is below that or above that, then the relay operates, indicating that there is a fault in the system or an abnormal condition in the system. So that's how a relay operates.
Okay. Anybody else would want to offer any additional input? Okay. We'll move on to the next question. This one be for Abel. Thank you, VJ. How are relay test switches and shorting CT terminal blocks used in protection testing?
Okay, hi everybody, I'm Abel. I've been with Megger for 8 years now. How are relay test switches and shorting CT terminal blocks used? Well, we're talking about 2 different things here. They're related, but they're not the same. The first I'm going to address is the last one, the CT terminal blocks and what are they used for. We know that when a CT is in operation, there is current, circulating to the primary of the CT. We don't want the secondary of the CT to open under any circumstances because of the high voltages that are incurred during that process, which can lead to personal injury, equipment damage, all sorts of problems in the system because the high level of voltage that's induced, which leads to a transference of power, a high transference of power. So we want to keep those CT terminals connected at all times. When we are doing, let's say, measurements, or when we're doing modifications in the system, when we're intervening in the secondary of the CT, somehow we want to make sure that those terminals remain connected during all of the, and that under no circumstance those terminals come unconnected or get opened. So the CT shorting blocks are strips of metal that are connected in the CT terminals, typically in the let's say in the back of the panel, the control panel. You will find the wiring where the CT terminals come, and then you have the wiring that goes up to the relay or meter or whatever application we are using that CT as a transducer for. And in that terminal, typically when you have more than one CT, all the terminals that constitute the non-polarity terminals of the CTs are typically grounded, and then you use that terminal block to connect those non-polarity to the polarity points of CTs using screws in a way that that connection is secure. Now, test switches, on the other hand, are used in the same protection and control and measurement panels to provide points for measurement of currents and voltages, to provide for points where we can actually inject currents and voltages into the relays or meters or fault locators, whatever equipment we want to test, and do so in a safe way, and even in some cases without having to interrupt the service of the system that we are, I don't know, performing those maintenance tasks in, because typically those test switches provide a way for us to safely take the equipment out of service without interrupting the circulation of current through the secondary of CTs, and give us the possibility of injecting currents into those relays and meters and other equipment without affecting the operation. I guess I've used a lot of time, but I wanted to. Yes.
Thank you. It's definitely a topic that you can get into a little bit more in depth, depending on the application. So appreciate that. Next question I have is for Sagosh. How do you recommend measuring and testing the burden on CT circuits for protection?
Okay. Hello, everyone. My name is Sagosh Kuber, Relay Applications Engineer with Megger. So thank you for the question, Eric. So let me start with the term burden. So burden basically is the total impedance in ohms on the secondary terminals of the CT, right? So any component, any circuit that is connected to the secondary of the CT, this could involve like relay coils, wire resistance, contact resistance, meters, right? Many other things. So to measure the burden, a rated secondary current is applied to the circuit, to the impedance that's connected to the secondary of the CT, and then the voltage is measured across the circuit to basically calculate the impedance and the phase angle of the burden. So once you have this, now you would want to compare this actual measured burden with the burden rating of the CT itself. So what burden test basically does is that it verifies that the CT can actually maintain the designated accuracy for a known load and the secondary current. And burden test is one of the important tests that needs to be performed as part of the CT testing in the field.
Thank you, Sagosh. All right, next question for Norman. Any suggestions to reduce the testing times and testing relays online without shutdown?
So if you look at some of the PSRC documents that are out there, you can see that every time you have a fault or an occurrence on a power system, you basically test that relay using natural signals. So if you go back and you look at let's say you've had a relay operation or you've had an external operation, relays usually have oscillography in them. So if you go and examine that oscillography very carefully, you can actually see if the relay is measuring the correct currents, the correct voltages, if it exhibited the correct behavior, etc., etc. If you actually had that there was actually a fault present and the relay operated, auto reclose came in, switched the line or the equipment back into service, Now I'm talking about lines only, not talking about transformers or anything. But if you look at those, you can then see, yes, I've exercised the output contacts, I've exercised the input contacts, the measurements are correct, everything's like I expected. Then you don't really need to go out and do a periodic maintenance on this relay, because basically the system has already exercised this relay. And by examining the event report and the oscillography, you can then verify that everything that the relay has done is correct.
Interesting, thank you. All right, next one for VJ. Back to you, sir. What are the most common relay failures? And this, I guess, could be pretty in-depth.
Sorry, I guess it is a pretty open question, because the common mode of failure for an electromechanical relay is completely different from a microprocessor relay. But in general, hardware failure might be a very common mode of failure in both the electromechanical relays and microprocessor relays. In the electromechanical relay, there's sensitivity issues, misoperation due to sensitivity issues, and calibration issues can also be pretty common. That's why the PRC 005 recommends you to test or maintain the electromechanical relays more frequently than compared to a microprocessor relay. In a microprocessor relay, the mode of failure is mostly the hardware failure. So when you're periodically maintaining it, you would check whether the outputs are working fine, whether your measurements are, the analog to digital converter is working fine. So those kinds of tests is what you would be doing. So hardware failure.
Yeah. Thank you, VJ. And last question in this particular category for Abel. How do electronic relays compare with electromechanical relays to perform the same protection? Describe loss of control power mitigation.
Okay. Well, that's an interesting question. It's also, I would say, an age-old question. So I have electromechanical relays, they're working fine. Should I replace them by microprocessor relays? The answer to that question is very hard from an outsider's perspective. However, microprocessor relays over the last 37 years, I think it's when we've had the microprocessors. We've had some sort of digital relays since the 60s, but microprocessors themselves, I think it was 83, 85 or somewhere around there that were actually introduced into the system, and they came of age, I would say, in the 90s. The reliability of microprocessor relays is so high when compared with all sorts of electromechanical relays that I believe that no installation, and I'm not going to say a new installation, no installation cannot benefit from the transition from electromechanical to digital relays. Microprocessor relays are faster. They are more repeatable. The repeatability is greater in microprocessor relays. You get a lot more information. The capacity of the protection systems that you can produce is way higher. I have gone into substations where, as a joke, I've taken a picture of 7 panels, one next to the other, and I've told people, see, all of those panels, you can replace all those operations with a single microprocessor relays. The operation, I mean, the basic engineering is easier to perform with microprocessor relays. I mean, the advantages are huge. Of course, all the electromechanicals, they are there. They always are, sensing the system. They don't care if they have power or not. applied to them. As long as there is a signal circulating through the system, the CTs are safe, are connected. They're always sensing the system. They can be maintained, I would say, forever. As long as you have someone with, I don't know, a watchmaker's ability, you can maintain an electromechanical relay. They will survive an atomic blast, I would say. So, I mean, there are things to say for both, but I'm of the microprocessor, I would say, induction. I like the other, everything that goes around that. And when it comes to the loss of control power, yeah, there are. I mean, when control power is lost in a microprocessor relay, you lose all the basic, and every protection function. However, there are ways to deal with that. You can create backup systems. I mean, a backup protection to back up that protection in that particular place. You can use fail-safe schemes to, I don't know, if you know or what you want, you can define what you want to happen when the control power is lost in that particular relay. If you have the threat of losing control power in a particular relay, you can use a self-powered relay, a relay that is powered by the power from the power system. I want to say something, though. I was reading when preparing for this particular question, I was reading about reliability, and it turns out that the loss of control power is even rarer than the loss of the microprocessor relay itself. And the loss of the microprocessor relay, when I say that, I mean the microprocessor relay failing catastrophically, is very rare in its own. So I guess I know I could talk about that for a long time. I saw that Norman was saying yes. I don't know if he wants to say something about it.
So I think if you look at the difference between an electrical mechanical relay and a digital relay, an electromechanical relay needs energy from the instrument transformers. That's why if you looked earlier, we talked about burden. So the burden that an electromechanical relay has on the CTs and VTs is a lot higher than the burden that you will get out of a digital relay. So digital relay just needs the information. It doesn't need any energy. So that's why you can see with digital relays, the trend has gone that the instrument transformers are also changing. We're starting to go with optical instrument transformers, like the optical CTs and VTs. The other thing that a digital relay does, it monitors itself. So if you look at it, there's a watchdog and all of that. The A to Ds monitor themselves. And if the relay is going to fail, it takes itself out of service usually graciously, right? It'll like shut down and strobe an output and tell you, listen, I'm out of service or something's wrong with me, so you can look at it. So I think if you look at the monitoring of a digital relay compared to a normal electromechanical, there is a difference to it. Now, Abel said that electromechanical or the analog relays were slower. That wasn't true. So we had, I don't know if in the US we had 3 stages of it. It was the electromechanical, and then we got the dedicated circuit, the electronic ones, that were built in the late 70s, early 80s. And those, some of them were incredibly fast. When the early generation of digitals came around, we introduced something called phasers. And the reason we brought in phasers is because the computation power at that time wasn't fast enough to process the data as it came in. So we created phasers, right? And we could go at a much slower rate. And that's originally, if you look at the original microprocessors, they ran at about a quarter cycle or so, because that took that long to do the data. And as the processors have become faster, you see the digital relays started to get faster. If you look at the digital relays of today, you get tremendous speeds out of them, and our sampling rates, like you'll get, it has been possible now to implement technologies such as traveling wave and get those kinds of speeds. That's because of the digital technology and to monitor it. So I would say there's been an evolution in digital relays, and the benefits brought to it are a lot more advantageous, especially in a power system that we have today. If you look at our digital relays today, and you look at our analog relays and our EM relays, we cannot really use our EM relays on systems that have a high ingress of inverter-based resources, because they don't produce the fault currents we need anymore.
That was something that I wanted to add as well. Adaptability to the system change. That is one major push for us to move towards microprocessor, because you can make the microprocessor relay or you can program the microprocessor relay based on your requirement. And in an electromechanical protection environment, that adaptability is complex and also painful to do.
Very good. Thank you, guys. All right, let's move on to the next topic, basic protection functions and testing. Sagosh, question I'm going to put to you. How do you validate time delay, curve, and multiplier setting on a relay?
Okay, so I would like to split this into different sections. The reason I say that is, a time delay setting is usually referenced with a definite time function. And then, the curve and the time del multiplier setting, they are used mostly with the inverse time function. So, the curves that are present in the relay that are used settings could be, the IEEE standard curves or IEC standard curves. So basically, when a particular amount of current is injected that is higher than the pickup value, right? So it can be 2 times higher than the pickup value or 3 times higher for that relay function that is being validated. The relay is supposed to, trip in a specific amount of time, right? And this time is dependent upon that curve that is being selected for that time del multiplier setting. So if you look at the time current curves graph, you would see that there are multiple curves that are shown at different time del multipliers. So, and those curves refer to basically nothing but time current curves, right? For this much amount of current, what is the time that is taken by the relay to trip? So with these time current curves, which are inverse in nature, higher the current means lesser the trip time, and again, like lower the test current means higher the trip time. So that is how we could validate the curve and TDM setting. And for the time delay setting, you would inject amount of current that is higher than the pickup setting for that relay, and then the relay is supposed to trip for by that time delay setting, which is either in seconds or cycles, and that is how those settings are validated.
Okay. Thank you, Sagosh. Mohit, I have an application question. How would you test agistat relays, and how many timers can you set?
Thanks, Eric, for the question. First of all, I think this is my first question, so I would reiterate on the same thing everybody said, like welcome everybody. We are really grateful to have you all here. So Eric is asking a question on agistat relays. We were having so much discussion on microprocessor relays, and then suddenly we are jumping back to the old age technology. But yeah, I would still answer the question, Eric. So agistat relays is typically those relays are used in the nuclear environment as time delay relays because they are usually adherent to seismic vibrations and all those kinds of conditions. So a lot of and they are also compliant with a lot of nuclear related standards. So many people still use those relays as for time delay functionality in them. And typically in my experience, what I have seen is there are like usually 2 types of agistat relays timers. There is like an on delay type, and then another one is an off delay type. So usually those agistat relays, they are, as I said, they're electronic miniature relays. So sometimes, I mean, they are electronic miniature. There are some models which are rotary type. So there can be different types, but I would like to answer the question on electronic miniature ones. So those electronic types of relays, they have this double pole, double throw contacts, so and then as I said, one relay itself can have like on delay type or off delay type, or the other relay can just have on delay type or individually off delay type. Basically, the question is how to test them. So on delay functionality is something like you apply a DC voltage to the coil of the agistat relay using any kind of test equipment, and then the moment you inject the DC voltage, the timer will start in a non-delay type of relay. And then when the set time based on what is the relay set for, if that time lapses, then suddenly your contact will have a changeover. So if your NC contact was initially connected, it will break, and then your NO contact will make. So you can set up something like in any modern test relay software. You can set up some timers, some state sequencers, where you can say, hey, pre-fault value of voltage is some rated voltage of DC, and then you can measure the time, how much time it takes, and you can compare that time against the set point plus the tolerance in the relay. The other, as I said, off delay type is a little different one. So it will, what it does is it will not start the timer the moment you inject the voltage. What it will do is you inject the voltage, DC voltage, and then the moment you de-energize it, the timer will start. So yeah, you can use something like you provide pre-fault voltage, and then suddenly on the fault state, you might need to provide no power, like 0 voltage DC. And then you can measure the time accordingly. So these are like some of the things I've seen with AgStats. And on your question on how many timers that can be tested, so I mean, I've seen modern test relay software can accommodate as many as 100 timers in a single test screen. So I think that should be enough for testing your AgStat ones, because they would not have those many timers.
Yep. Thank you, Mohit. Appreciate that. All right, next question I have for Abel. How can we protect the measuring inputs against voltage transients, mainly caused by atmospheric discharges?
Okay. Well, I guess the answer to this question should be, in my opinion, split between two different things. The protection relay should be able to measure properly even in the presence of transients in the system. And the second is, how do we protect the physical relay from damage against those transients happening in the system? The answer to both is a combination, I guess. To the first one, you have a combination of hardware and algorithms that filter digitally and physically the signals that go into those measuring inputs and provide only the signal to the relay that is relevant to the measurement that is being done at the moment. Those algorithms are well known. We have cosine filters, and we have other ways of filtering or taking the fundamental magnitudes and whatnot. And there are other types of relays that I guess Norman can talk about them later when it comes to different I would say fundamentals that are being introduced in the last few years of measuring and protecting in the system, and to how to prevent damage on the voltage and current inputs in the relay. There are standards both in IEC and IEEE that those relays and those standards have, I would say, tightened over the last few years. And relay manufacturers, in their specification sheets, they declare which standards they comply to when it comes to electromagnetic immunity for both the relay inputs, whether it is the relay voltage inputs, current inputs, and also the actual inputs and output, the digital, which are also subject to those electromagnetic events in the system.
Can I add one more point? I think if the question is related to like how do the CTs and PTs, those are the measuring inputs. The question is how do you how is the measuring input being protected against an atmospheric discharge, which is like lightning or something. So I think if the question is that, then probably each CT and the PT have its own saturation point. Beyond that saturation point, it doesn't provide any secondary current into the relay. So your relay is either protected that way. And also on top of that, you have the ratings of the instrument itself. So beyond a certain value, like 100,000 volts, then probably your measuring device itself is going to fail.
So I think what we got to be careful of here is if any device gets a direct lightning strike, Vijay, it's tickets. Nothing is going to stop it. It's got to do with energy. So all protective relays, like Abdul said, is we comply to 6255, which is the IEC standard for surge immunity. So all of the inputs in that are tested for that. We have 10 kV discharge tests and all. So the relay is tested for all of those, and you have to pass those immunity tests. They -1, they -27 and 26. So if you look up to 6255, and if you look into the relay specifications, we say we comply to the following, all of those. Now, I think that's what the question was about, is how do you sort of prevent a misoperation if someone goes past and you touch it, or you have a static discharge to it. A static discharge isn't going to create a relay to misoperate. They've been tested for that, right? They're not supposed to. But if you get a direct lightning strike into any piece of equipment, right, your surge arresters may be there for a short while, but they don't have the energy to dissipate that. You're probably going to have a bit of damage on it. And if you get a direct lightning strike into a relay, there's nothing you can do. That's why if you look at most of the installations, you have shielded wires, so you want the lightning to go into those rather than going to even your primary equipment.
Yeah.
So I think within a substation, I don't think that if you do a static discharge, you're going to get a relay to misoperate. Okay.
Thank you, Norman. All right, next question I have for Sagosh. This one is a pretty vague question, so I would try to keep this one to a minimum. How to test differential relays? There's a lot of parts and pieces to this, so have at it, Sagosh.
Yeah, thanks, Eric. Yeah, this is a very generic question. The reason I say is differential protection can be used to protect generators, motors, transmission lines, right? Bus, can be anything. So the approach also depends on what kind of relays are being used to test, right? Electromechanical relays or microprocessor relays, the single phase or three phase relays. So anyway, to answer this question, I'll stick to transformer differential relay testing. To perform the test, of course, you would require like 6 sources of currents if it's a 3-phase injection, or to mimic currents on both the windings of the transformer that the relay is reading. If it's a single phase, you would just require 2 current sources to inject the currents, right? And a lot of factors come into picture, like the transformer winding configuration, how the CTs are connected, and the relay settings, right? So based on all these factors, the currents that needs to be injected needs to be calculated, and then needs to be injected to the relay. So some of the important tests that needs to be performed for a differential relay is, one of them is stabilization test. What this test does is basically tells us that for a balanced set of currents, the relay is stable. It is not tripping for that balanced set of currents it's seeing. So it tells us that our currents that we are calculated are correct for the injection. And the second thing is the wiring connections are good with the test set and the relay. Next few tests would be to perform a pickup test to validate the pickup setting of the relay, and then we perform like a slope characteristic test to validate the operate and restrain regions on the characteristic itself, which of course depends on the slope settings in the relay. And then we would also perform a harmonic restraint test to validate the harmonic setting of the relay. And again, like I said before, these things would vary depending on what kind of relay you have at hand and what application they are involved in. Hope I answered that question.
No, like I said, it could take a lot of different applications. So thank you for going into transformer a little bit. Next question I have for Norman. How do you protect distribution feeders with added distributed generation?
In a nutshell, you do them exactly the same as you do transmission lines, right? So if you look at transmission lines, we have to deal with generation in the transmission lines. And so if you have distribution, so I think the philosophy that we used to have for transmission is now going to be a philosophy we're going to start applying to distribution. In that way is that we don't have power flowing in a single direction anymore. We've got bidirectional power that we're going to have to look at. So we are going to see functions like even distance being applied, directional overcurrents, line differential. So I think that we are going to see a lot more of that come into distribution as now, in that the power is moving in both directions. So I think we are going to start seeing distribution schemes that look very similar in nature to what we are used to seeing in transmission. That's in a nutshell.
Okay, no, thank you. Appreciate that. Abel, next question. Can you talk about how capacitor banks are protected and what are the main types of protection function used?
Okay, yeah, this is the, well, like many other questions, this is a question you could give a long answer to. The capacitor bank is I would say, deceptively simple device in the system, because it's something you say, oh, it's a capacitor put in shunt with the system, but the way capacitor banks are built means that there are many different ways in which they can fail, and therefore there are many different things to protect for, and there are many different ways in which you should protect them. So you have to, the first thing you have to know is which type of capacitor bank you have. Is it a single Y? Is it a double Y? Is it a single Y ungrounded? Is it grounded? Depending on that, then you choose the type of protection. The basic, I would say, protection used for capacitor banks is the on-balance protection. Now, when it is stated like that, in that general way, because you can have on-balance protection, voltage on-balance, you can have current on-balance, you can measure the neutral voltage in the ungrounded capacitor banks. You can measure the difference in current between the neutrals. If you have a double Y, you can do a voltage differential. There are many different ways in which you can do the the capacitor bank on balance protection. I have the number here. There is a C3799 IEEE guide for the protection of capacitor banks. The latest, I would say, issue, or because there was a number from 2000. Now there is a 2012, which is the current one. And in capacitor banks, of course, you use all other sorts of protection. You use overload, you use overcurrent, you use earth fault, and other types of protections in combination with that protection. And of course, you have the control of the capacitor bank. You have the harmonic. There's a lot of things to be said about capacitor bank protection. I guess to keep it under.
No, thank you.
I would just like to add one thing on that. I think Abel missed the word differential. So like neutral unbalanced differential is one kind of protection that I have heard of in capacitor banks, like for ungrounded Y applications. So you put you have a VT connected on the ungrounded Y side. So basically you measure the voltage of the neutral and ground, and then you compare against the phase side PTs, and then if there is any kind of fault in between, that voltage differential will kick in, and you can have your protection. And another one is like phase. Similarly with the neutral ones, you also have, as Abel mentioned, depending on the application, phase voltage differential is also present if you have grounded applications. So. Yes.
I think what we should say is different on capacitors. You don't take a capacitor bank out of service if you have one capacitor fail. You allow a number of failures, and when the imbalance becomes too high, then you take the bank out of service. So, and it's also another thing that's very important is whether the cap banks are fused or fuseless, right? That also has how you do the actual thing itself. But it's one of the more unique that you don't take it out immediately. You measure how it fails gradually, and just before you get to catastrophic failure, you remove it.
Yeah, there's a whole array of protection involved, from, like you said, fused, unfused versions of just the capacitor itself. So thank you, guys. Next question, Sagosh. How to validate earth fault and how to check relay sensitivity. So I guess this could tie together with this cap bank question a little bit.
Yeah, thanks, Eric, for the question. I'll start with the term sensitivity. Sensitivity of a relay is basically its ability to operate for even the slightest of the faults that is within the zone of protection. Like if you consider, like for example, restricted earth fault, right? So it provides sensitive protection to a zone between two measuring points against earth faults. So the logic that is implemented for this, in the earth fault for in relays can be different from each other. So I would stick to one of those implementations for explanation purposes, wherein the logic basically uses the 3 CTs. Let's consider this earth fault for a generator, earth fault protection. So the logic uses the 3 CTs at the generator terminal end and a CT that's placed at the neutral point of the generator. So your zone of protection lies between these CTs, right? And then the relay is connected in such a way that it monitors the currents from the neutral CT as well as the residual current that's caused by unbalance from the phase CTs. So when we talk about zone of protection, we know that whenever there is an external fault to this zone, the relay is not supposed to trip for that particular true fault. Whenever there is an internal fault to the zone of protection, the relay is supposed to take care of that fault, right? So this particular logic, it operates on directional, which basically uses one set of current as the polarizing quantity, for one set of CT, and the other current would be your operating quantity. So when testing this particular relay, right? So the way you would inject the currents such that the magnitude and direction, when these are for both the quantities, are compared with the setting on the relay, right? The pickup setting on the relay. And depending on what type of fault you're mimicking, if it's an internal fault to the zone, the relay will trip. So this is how we can validate an earth fault relay. And like I said, the way the logics that are made on these relays could be different from one another. So you would have to look into that as well.
In general, how do you define the sensitivity of a relay? You inject a small amount of current on the operating coil, and then you increase that until the relay operates. When the relay operates, the value is that sensitivity of the relay, without any external forces trying to reduce the operating coil operation.
Okay, thank you guys. Next question I have for Norman. Why would an engineer specify a delay of 1 cycle on an instantaneous element?
That all has to do, so let's assume you have a very weak sort of system and you could get possible CCVT transients. So you say, instead of my zone 1 going immediately, I could get an overreach on the zone 1. I'm going to say a CCVT transient might just last 1 cycle, so I'm going to delay my zone 1 distance element by a cycle. So that's to avoid something like an instrument error that I can get, like during a CCVT transient. The other thing is, it's got to do with if you get a certain overreach or overshoot out of an element. So what could happen is if you have your filter is very high speed or something like that, and you can get a certain overshoot and you want to go for a certain amount of sensitivity, then you might want to delay. So delays are there done more for security than for anything else, right? That's to give you that increased security. So for example, like I just mentioned, for the zone 1s, you might say, okay, I've got a very strong possibility of a CCVT transient here. How do I prevent a misoperation for that? Well, I delayed this element over here. There are smarter techniques you can do it with, but that's one of the conditions that you can actually do that for.
Okay, thank you, appreciate that. All right, Sugosh, another question for you, sir. When testing differential relays such as ABB, Westinghouse, the HU and HU1, do you prefer automated test or manual testing, and why?
Okay, it's an interesting question. So automated testing, right? An automated test plan basically would communicate with the relay and then read the settings, and depending on your test that you have enabled in the relay, the elements that are enabled in the relay, it would calculate the test values and then apply those test values for the testing and then report the results, right? So this is how I would define an automated test plan. When it comes to the electromechanical relay, it would be termed semi-automated, I would say, because there is no communication involved here. So user would be entering the relay settings manually in the test plan. There are ways you could make the test connection for this relay in such a way that changes in test connections are not required after each test. right? You could make that connections once and for all. Of course, you would still need to block the harmonic unit when you perform differential test, and the differential unit vice versa, right? One at a time. So, but when you have all these connections made at once and have a semi-automated test plan, I mean, why not use it, correct? So, of course, the semi-automated test plan is preferable. When it comes to manual testing, of course, the test technician here would need to perform the calculations needed for performing those tests. And again, even manual testing would work as long as the tester is comfortable doing that calculation and has the time to do that. But let's say you want to repeat this test, right? There are multiple relays as part of your maintenance program. Of course, you would want to probably have a semi-automated test plan. So then you don't have to do the calculations and all that. So that would be my answer for this question.
Okay, thank you. All right, we're gonna move on to the next section of testing called Advanced Protection Functions and Testing. Bell, I have a question for you, sir. How to test switch onto fault protection testing in a distance relay? How do you test?
Well, that's a tough question because there is no standard defined switch onto fault logic that you can say this is the way to do it. So my first recommendation would be verify what logic are you testing for which remember that there is something called the art and science of power system protection. I know that there are standard guidelines of what switch into fault protection is supposed to protect against, right? But there are many different ways in which the logic could be implemented. So I guess the first answer would be verify what the logic that you are testing has. Now, every switch into fault logic would have something like the breaker is open, it closes, and when it closes, it detects that there is no voltage on the line when there's supposed to be voltage on the line, and it should trip instantaneously, and that logic should be alive for, I don't know, a set amount of time, and after that it should be disabled, right? So I guess the way to test it would be to consider those conditions and create a test logic that allows you to do that. Typically, you would do it using something like a state simulator. You also need to simulate the breaker status for the relay to know if the breaker was open, and then that the breaker close command was sent, and then you need to verify that the trip command was sent properly to the test set, and then you will compare. I'm trying to keep it as I don't know, generic as possible. Because like I said, it's not like an overcurrent where you say, I inject 5 amps. If my pickup is 2.5, that's multiple 2. I compare with the curve, and that's it. It's not exactly like that. It depends if you are in a recloser, if you're testing on a transmission line. If so, I would say the minutia of how that function is defined or designed in that particular relay have a lot to do with how you perform that test, I guess. Yeah.
Thank you.
Norman.
So if I may add.
Yeah.
So if I may add, just quickly, why is the switch onto fault logic? It's there mostly for distance relays, because what will happen is if you energize a line, like you correctly pointed out, and there's no voltage present, your distance elements can't work, right? So there's two conditions you usually check. Is a switch onto fault for the fault right in front of you. Then you rely on your 51 elements. And that's a non-directional. That means if you close the breaker for a short amount of time, you're going to say, if this current exceeds this threshold, I'm going to trip. Irrespective of that fault's in front or behind you, you've got no directionality. Then there's the second one, which you test for. That's for the fault at the end of the line. So what you do is you have those two conditions and you check. And what you don't want to do is have a compromise in speed. So in the switch on to fault, if you do pick up a zone 2 fault, you then trip immediately. So that is to clear a fault as quick as possible that's on the transmission line. That's the purpose of a switch on to fault. Okay.
Thank you,
Okay.
Norman.
I think,
Appreciate it.
okay, sorry. Thanks, Norman.
Go ahead, Abdul.
Thank you. Norm, I have another question for you, and since this is in regards to some Schweitzer relays. How are the word bits assigned to transmit on different faults?
The word bit, so are they talking about particular phase faults or whatever? So what we do is we have a fault identification logic. And that's if you're going to talk about, let's say, you're going to do a POTT or a DCB scheme, and you want to do single pole tripping, right? And this has to do if you have inter-circuit faults or so, and I want to make sure that I trip correctly. We do send phase-specific information to the other ends. So our communication schemes, like a POTT, will say, right, I see an A-phase fault. And if the other guy says, I see a 2, then we'll trip single pole. So there's a lot more to this. We have word bits for almost any sort of logic. And you can transmit what you want to across it, right? So we have, so if you have an 87L function and you have extra space, or we have mirror bit that you can send stuff to the other side with to give you better tripping or to give you better discrimination. That's what those word bits are used for. I hope that answers this question.
Yeah, and that was I'm trying to understand if it's communication protocol type of an application or how it was applied.
Okay.
Thank you. All right, next question I have Sagosh. How do we ensure that relay testing mimics real-world events, such as faults, and not just testing elements for the sake of testing them?
Okay, this is a good question. You know, in order for you to mimic real-world conditions while testing, I would say, you would want to, first of all, model your power system in a simulation software. You know, wherein you build your power system like on the software pretty close to what you have in the system, right? With all the factors considered, and then you would simulate different fault conditions on the system, and then you know, for different scenarios of fault conditions, and then you can export completed files from the software for these scenarios, right? So these completed files basically would have the test values which actually mimics the faults that you simulated on the software. So once you get these completed files, you could use them to play back onto your actual system, actual protection system schemes or relays to mimic, you know, almost pretty close to what you would see on real world conditions. Another way to do this is you could also get the SS1 files for these fault scenarios you simulated on software. And then these files basically consist of all the fault simulations built as state sequencer tests. And again, each of these states have, you know, voltages and currents that actually relate to a type of fault that you just simulated in the software. And once you have these files in the form of state sequencer tests, you could again, like, you know, perform the test using these files. And again, by doing this, you're not just injecting some current and voltage into the relay and, you know, checking that particular setting, but trying to simulate a fault condition which is at least as close as it can get to a real world condition, right? But based on the studies you just performed on the software. Hope I answered the question.
Yep, thank you.
I want to say something about that, if I may.
Go ahead.
I want to add that to what Sugosh said, that if you want to really test, you have to, in my opinion, expand your mind from testing the relay to testing the system in which the relay is supposed to operate, and go from, you know, single relay, because we were in element testing, then relay testing, and then, but is that what we really want to test? Or do we want to verify that the relay or the protection scheme is working as intended? You know what I mean? Because testing the relay or testing the element only verifies the element or the relay, but we don't know how the protection system is actually going to behave. So what I'm trying to say is that for that particular question, I think we should expand our scope of testing from single element to relay and then to system testing. That I would guess is what I want to say about that.
Okay, thank you.
So So can I just pose a question? Is that commissioning testing, or is that got to do more with a FAT testing?
Well, when you're talking about the factory acceptance test of the relay, or are you talking about the factory acceptance test of the, I should say, I don't know, the power cell, the panel?
The panel.
So what I'm
Yes.
saying is, when you do a FAT, that relay is put into a larger system, and then the relay is tested as a whole in the system. And I think, Eric, I don't want to, but if we go to the next question, I'll tell you why this becomes important. Okay, let's hold on here.
Yep, and that's where I'm going to jump into the next one. How to test power swing block for transmission line, Norman?
Right, so here it goes, right? So what is a power swing? A power swing is where it happens, and you can get a stable and an unstable swing. So we have to be very careful. Then we've also got to say, are we looking for a generator or a transmission line? So let's look at a transmission line as a whole. So a power swing occurs when the amount of energy or the power produced and the power consumed are not the same, right? And so what happens is, let's assume that I have a power plant that brings out 600 megawatts. And all of a sudden I get a fault and I only push out 400 megawatts, right? Now those 200 megawatts, they don't just disappear suddenly. So they go into accelerating that machine, right? That gets into kinetic energy, it gets stored into rotational energy. As soon as that fault clears, and that now it becomes very careful, is how long does it take that fault to clear? When that fault clears, now you've got an excess amount of generation in here, or excess amount of stored energy in this generator that you now got to push into the system. And you now start getting these watts of power starting to move back and front in the system. And if you want to test this properly, you've actually got to say, like what Gersh and Abdul says, you have to model this in the dynamic system. So you have to model the generators, the AVRs, and the actual governors. And then what you do is you actually create a fault condition, right, on the system. You then clear that fault, you're going to get a swing. Now, whether it's a stable or unstable swing has to do with the duration of the fault and all of that, how long you keep it on. So ideally, you don't want the system now to fall apart. And so what you have to do is you sometimes have to watch this over 2, 3, 4, 5 seconds to see how the swing and how the system goes, right? And that's why you have functions called power swing blocking. So you have to do them realistically, because some of these relays are settingless. What they do is they measure the rate of change of the impedance of the element, okay? And what you ideally want to do, if you know this is a stable swing, or even if it's not an unstable swing, you don't want to immediately trip. Because let's assume that if you do have a swing and it's an unstable swing and it goes through your transmission line, you don't want to trip at that moment, because now your systems are 180 degrees apart. If you trip those breakers are going to come apart in pieces because they cannot handle that voltage difference. So you have to wait a certain amount of time. So when you actually want to test power swing, the best way to do it is actually to model this in an EMTP sort of fashion, if you really want to test it. And that I would say you do in an FAT. But if you're going to just check that this function works in a relay, or you're just doing a commissioning test, then you don't have to go through all of that. Then you can take just a simple, if you wanted to just create a few states, but that's not going to give you an accurate representation of what that system will do. If you want an accurate representation of what the system is going to do and how your relay behaves, you've got to do that in an FAT. That means you've got to model the dynamics of the system. What's very important, what's the inertia constants of the two systems, because that'll tell you how long it'll take for the system to accelerate and how long it'll actually take to get back to stability. And you've got to actually monitor that relay throughout there, okay? So there's two things you test. You test out-of-step blocking, if that scheme has to do blocking, and then you have to test out-of-step tripping, okay? So those are the two things that you probably have to test.
Thank you very much. I mean, like I said, there's a lot of content, a lot of information that go into a lot of these topics. So appreciate you guys trying to keep them as simple, but without the integrity of the answer. So I know we've reached the end of the scheduled time. However, we've got several more questions, and I believe we want to continue for about another 30 minutes if those who would like to continue through this process. And the panel, obviously, we're prepared to address as many questions as we can. Abel, with the next question, how do infeed and outfeed affect distance protection?
Well, let's remember how distance protection does its job. Distance protection, what it does is it measures voltage and current and determines how much impedance the relay sees in the line at any particular moment. And using that impedance, the relay knows whether there is a fault or if the current that's circulating through the system at that time corresponds with the normal circulation of load current. When there is a fault, the angle of the current typically jumps up to the angle of the line, because when there is a fault, the current that circulates is mainly because of the voltage in the line divided by the impedance of the line, and that way the relay knows that there is a fault, and if the fault happens at an impedance that's lower than a particular number that has to do with the size of the line, the relay operates. Now, when we have an infeed or an outfeed, which essentially are two, I would say, names for something that's very similar. It's a tap that you have on the line where you either connect a source that's providing power, or you connect a load that's drawing power from the same source that the line protection is trying to protect. If you have an infeed, that means that you have an extra amount of current that is going to, I don't know, be circulating to the fault point. Unfortunately, we don't have a visual aid, but what happens when you have an infeed is that the relay estimates that the impedance that is that the impedance of the fault is actually lower than the actual. I'm sorry, higher than the actual impedance. Thank you, Norman, for the save right there. And the reason for that is that there is current that is going into the fault, and the current that's circulating into the fault raises the voltage profile of the line, and therefore you have an apparent impedance that right now looks like it's greater than the impedance that that the actual impedance of the. Now, when you have the other case, which is the case of the outfeed, that means that you are supplying current from the same source that's supplying current to the fault. You are supplying an extra amount of current that is being supplied to a load that is connected at a point where, and then now in this case, now you have a current that's higher than the current for the, let's say, for the only the current that would circulate if there was a fault, and therefore you have a measurement of impedance that's actually lower than the impedance that you would measure if there was no tap and the fault was wherever you had that. So you have to take those into consideration when you I don't know, set your impedance protection in the relay, and I guess that's it.
So in a nutshell, outfeed, right? So if you have an outfeed condition, you're going to you're going to overreach, right?
Overreach, yes.
You have
underreach.
An infeed condition, you're going to underreach. So if you want to do this very quickly, just draw a 3-terminal line, okay? And put a fault very close to one of the terminals. And then what you do is from the left, so name them A on the left, B and C at the bottom. Then what you do is you let the current that goes to terminal C either flow towards terminal C or out of terminal C, toward that fault point close to B. And what you will see is when you have that current from A and B flowing in the same direction, the voltage drop you get across that from the T point to terminal B is going to be much higher, because you've got the two currents the same impedance, right? So it'll be much higher. So the voltage that goes back at the relay you measure is going to be higher than you would have normally had. When you have an outfeed condition, that means that the current at terminal A and terminal C are flowing in the opposite directions. That means currents flowing into terminal C for the fault. Then you are going to get less current flowing between the tap point and the fault point than what you would expect, and you're going to get a lower voltage, and therefore the voltage will be lower at your terminal you're measuring at, and therefore you're going to think when the voltage is lower, the fault is closer to you. So therefore, you're going to overreach, and therefore you'll have a misoperation. So all of these have to be taken into effect for when you set the distance. Now this is for, I mentioned the 3-terminal line, but when you have your zone 2 element, you have to definitely take into consideration the infeed and outfeed. That's more dominant in your zone 2s because you've got your other feeders that you can either either feed in or you can feed out to those other feeders. Does that make sense? Abdul, you look like
yeah, for sure.
Right. This question's coming back to you as well. What is the method to verify fault locators?
So fault locators, I mean, if you want very accurate fault location on there, you actually have to, and this is now, do you want to do it in the field or back in the laboratory? So if you do it in the field, you would actually do this with known test quantities. So what you do is you would say with these test quantities, I've got to measure this impedance. Now I'm talking about impedance-based fault locators, and they've also got to do now, are these single or multi-terminal? If these are multi-terminal fault locators you're going to have to do, this is very similar than what you will test a line differential with. You will take a known quantity of voltage and current at a specific location, and you will put them, you will then load those into both of the relays and trigger them at the same time. And then you measure what is the impedance measured by the relay or the distance given to you by that relay, all right, for each of the relays. And then you say, this is the measurement I expected, and this is the measurement I got. This is my error. Okay? So that's how you would do it. You have to apply known quantities for a specific location. So what you would do beforehand, you would say, okay, I want to have a fault location at 20% of the line. Then you've got to go in and have a look and say, okay, I'm going to apply these quantities that give me an impedance that is exactly equal to that. Now, this is all ideal. Okay, so you'll go for a solid fault, all of that. You won't go, if it's a single-ended fault locator, you're not going to do this with infeed from another source. It's going to be a single-ended only, all right? Because if you're going to try and do a fault location with having voltages on 2 terminals, then exactly what I explained to you is the infeed-outfeed condition, because the infeed from the other terminal is going to boost the voltage at the fault point, which will boost your voltage, will give you the incorrect impedance, which can give you, if your systems are not homogeneous, will give you an incorrect fault location. So fault location is done with specific values at specific locations on the line, and you have to compare them. Now, there's a newer technology that's available. It's called traveling wave. And for that, you need specialized test equipment to do it. And the only way I've actually seen this being done is actually live. So they'd go to a certain part of the line, and they would actually shoot, they'd actually create a fault, either through shooting a very thin copper wire with a crossbow over the conductors, create the fault and have the fault vaporize, and then they will look back at it. But most of the impedances that you'll test today for fault locators will be impedance-based, and therefore you will need accurate voltages and currents at specific locations, and you've got to check those. And then when you get your fault locations back through your fault locator, you have to look at, this is what I expected, this is what I got. That's how you have to test fault locators on this. Okay.
Very interesting. Thank you. All right, next question. We're going to get into some IEC 61881 or 850 topics. Abel, how are utilities managing cybersecurity for relay test sets, relays and controls and substation, not necessarily BES related?
How much time do we have? I think that was the. No,
Yeah.
I'm just joking, because Mohit today, when I asked him to address a particular question, he said, how much time do I have? And I need a week for that. This is a tough question. And the thing is, when I was thinking about the answer to this question, I was thinking about a phrase that I heard many years ago when I was taking the classics, Hannibal ante portas. It's when Hannibal was at the doors of Rome and everybody was afraid. And the thing is, the cyber threats are real. They are there. They're not as bad as we would hear from but they're not also in the false sense of security that you see many people having. No, I'm safe because I'm doing it. I think it's a compromise between both. I know that NERC, for example, they have a lot of requirements. The person who asked this question said not necessarily BES related. I assume he's talking about non-NERC utilities perhaps. The thing is that even those utilities that are not NERC, they are looking at somebody's, set of guidelines to help them understand how to protect their cyber assets. I have seen over the last few years utilities become tighter and tighter when it comes to the separation between their operational and information networks. I have gone to tried to help somebody to use a computer with our software, and they have to use a computer with a camera and show me the software installed, our software installed in another computer that they cannot connect to the network because of that separation between both networks. That's one way that I have seen that separation. However, there are people who say that separation is actually not a reality, because a lot of manufacturers have built backdoors into their systems, and they even require and include that in service level agreements that those equipment need to be connected to a network in order for the manufacturer to be able to provide a service to those equipment. I have seen, for example, the question is about the test sets. I have seen requirements from utilities where they tell us if our test set has some sort of electronic signature, that even if the test set is compromised, the software will revert to its original state that identify the threats during the boot up process of the software. I have seen them, for example, prevent the use of USBs in computers. That's something that they're doing. They cannot. A lot of our customers tell us that they cannot use the USBs to take the information out of the test set, because then they have no way of plugging them into their computers and use that information. So we have had to provide other ways of accessing the information that is on our test sets. Now, when it comes to the relays, which is another part of the equation, the relay manufacturers, and Norman can perhaps talk to that, provide several levels of security. They provide all sorts of password management and user management and whatnot. But it is up to the utility to use that. And the question is, are they? How many times you get to a relay in a substation and you know the password that relay has, because you know that that's the default password of that relay and that it has never been changed and it will never be changed in the life of the relay. And even if it has, all you have to do is open the relay panel and the password is written in the back of the I guess the other thing that utilities are doing is they're becoming aware of those facts, and they are going into education, because when you read about reliability, the human factor is typically the highest cause of cybersecurity misoperations and all sorts of troubles in the system, because we design the systems, we engineer them to be intrinsically safe, but then there's a human who is operating the system, who has to be able to follow the recommendations and requirements, and unfortunately they don't, and that's where I would say a lot of these lies. And yes, the enemy is at the door. We just have to be conscious of that and take the proper.
Yep. Thank you, Abel. And then we wrap up this last question in this section for Mohit. How to test a digital substation with IEC 61850 implementation, such as interlocks, goose messages within the same or different IUDs, etc. And please try to keep this minimal too, please.
I think, yeah, Bell started with this point of implementing cybersecurity in the system. So cybersecurity is one of the key areas of digital substation. Now, talking about the testing, so I would like to classify this question into two types of testing. One could be like a functional testing, where what you can do is you can have a testing equipment, you can have an IED compliant with 61850. So Goose is basically 8-1, or it could also have sampled value compliance, so 9-2 LE. So what you can do is you can use your test set in that case, which would also be compliant with the and H2LE. You can generate sample value streams into the relay, which is sample value compliant. And then basically you can have a goose signal connected from your relay and to your test system. So in all this whole process, the goose signal can act as like a sensing of any trip functionality. So this is a straightforward functional testing. So in this kind of testing, you don't require any physical wire connections, right? So you use Ethernet switches to provide a sample value stream. You push it through that. Now, keep in mind that those Ethernet switches cannot be like unmanaged switches. You try to keep it managed switches so that you can control some kind of priorities if it's a big substation. So then in that case, you need to configure different VLAN IDs so that you can, prioritize some signals over other signals. So those things have to be kept in mind. But for functional testing, one-on-one bench testing, you can avoid that VLAN stuff. The second part of the testing that I want to talk about is maintenance testing. So maintenance testing would be one type of testing where if you have to detect if some kind of misoperation happens in the system, you have to detect it, but in an energized condition. So how would you do that? So the future of the testing is also moving in that direction. Now we have 62850 8-1 62850 edition 2 standard, which has more capabilities of providing a relay in such kind of modes where you can test the whole digital substation when it is energized. And it will also, the standard is also pushing different relay manufacturers to be compliant with it, so that there would be no challenges related with interoperability. So in that kind of system, a field crew doesn't need to go to a substation to do some kind of testing. Even remote testing can be performed. So you can install some test equipment which is compliant with those kind of standards into a substation, and you can have that IED which is compliant with those additions in the substation, everything connected in your control room or wherever, and then you can use your test system at your operation room, maybe like a computer. You connect everything through either fiber optic channels or Ethernet cables through Ethernet switches, and then you can basically automate everything from remote end. I think there is also some work going on in a CGRE working group. I think it is B5 or something. I will double check, but I believe it is B5, where this kind of work is going on, talking about remote testing, the testing I'm talking about. So in that kind of testing, even if the system is energized, you can set a relay into some modes like test mode, which these relay manufacturers say. And under these test modes, you can provide, you can mimic signals without compromising the breaker operation. So those kind of features are also available, which you can test the whole. I mean, there are some technical terms there like logical nodes and logical devices without compromising the breaker operation. So that, in a nutshell, you can do the whole digital substation testing, like the scheme testing, in an energized environment. And a lot of work has been going on right now in those lines, those areas. So yeah, I think I would like to wrap here with that one.
Thank you, Mohit. All right, then we're going to move on to this last section called maintenance. And first question I have, it's kind of a combined set of questions for VJ. How often should protective relays be tested? Are there standards that can be referenced about the frequency of testing? What are your recommendations for maintenance on non-NERC microprocessor relays, such as test intervals, what to test, load check, etc.? It's kind of a long question, but do your best, sir.
Okay, sure. The standard that is associated with frequency of testing is the PRC 005-6 that was out like a couple of years ago. What they mention is any unmonitored devices like the electromechanical relays, which doesn't exactly have the self-monitoring capability and also transmitting the alarm signals back to the SCADA system. Those kinds of unmonitored protective relays, they need to be tested every 6 years. what you check on those is you verify the settings that were implemented during commissioning, or whenever it was last changed. So you verify the settings. If it is calibration needed, if at all any calibration is needed for the electromechanical relays. And for a microprocessor relay, basically you test whether the outputs are working fine, whether the ACDs, the analog to digital converter is working fine, those kinds of components testing on the microprocessor relays. When it comes to the monitor devices, you test every 12 years. Basically, you test the same thing on the microprocessor relays. In the protection system, communication is also included. I think the unmonitored communications have to be tested every 6 months, or I can verify that right now. 4 months, and the monitored communication systems have to be tested every 6 years. That's the PRC 005-6 standard.
Okay. Thank you, sir. Next question I have for Norman. We have a couple questions left we'll try to fit in here. The SCL 751A overcurrent relay manual says the 751A does not require specific routine tests, so no PMs needed if constantly self-testing.
So as I mentioned before, right, digital relays basically monitor themselves. Okay, and if you don't need to test it. If you go in front of a relay and you do a meter command and it measures the rate, voltages and currents, you're fine, because everything else from there goes through the algorithms. Okay, that means if you do the metering command, you've basically verified that the A to D is correct, that everything from that point is correct onto this device itself. And if you do an overcurrent, what's an overcurrent? If you're reading the right currents, you know that if you get an overcurrent condition, you'll get the right measurements out of it. So as I said earlier, you don't need to specifically go out and test these functions. The only thing that happens is if you don't have a fault or you do the metering, the only thing that you can't test is the output contact, all right? So it could be that the output contact could be broken, right? So everything will be correct up to that point to the output contact. That's why I said if you have, let's say, have a fault on the system and the relay operated correctly, then that's all you really need for that time period. But to go in to inject quantities to make sure that they are accurate, that's really pointless. I mean, if you go to the metering and you know from another device that this should be the correct current and it reads that current, you're fine. Okay, and it's not just an SEL relay. I think that goes across the line for all digital relays in themselves. Yeah.
Okay. Thank you, sir. Vijay, back to you. What are the advantages of a single test block for current voltage test in contrast to individual test block testing?
I'm sorry, I didn't. Abel, do you want to take it?
Okay. So the question is, what is the advantage of a single test block for current and voltage test in contrast to individual test block testing? I would assume that the question is, when is it better to use a test block that has both voltage and current, and other cases where they have a test block that has only voltage and only current? And I'm going to say that depends on the application, the design, the engineering. Some applications require that you have both. Some applications require that you have only one. In some places you have a lot of room, and other places you don't have a lot of room, and you have to make it as compact as possible. If I have the choice, I would choose to put the currents on one side, the voltage on the other. That, in my opinion, makes it safer from a design standpoint. But I have seen both in the field, and if you know what you're doing, you can safely operate and test and do everything without any difficulties. I guess that's what I have to say.
Abel, I would add one thing, right? If you're going to if that test block belongs to a distance relay or impedance relay, make sure you pull the current test block first, right? Because you can have an impedance relay have no current and voltages, but if you pull the voltage test block first, you could get an operation. So I think there is an advantage to having them separated in some cases.
Having them separated, yeah, that's what I would do always. Okay.
All right, and I think we have time for one more question. Let me pull up this sheet here. VJ, I'm going to give you an option. Let me grab this one here. What is ideally good for monitoring breaker trip coil or circuit by using protection relay wiring setup or by using external dedicated trip coil monitoring device?
My answer would be, it depends.
Our new Alex.
Yeah, I know. That's what Alex would say. It depends on what the requirement here is, and the most breaker control relays have their own trip coil monitoring system. Again, Norman mentioned many times the relays themselves monitor, and these trip coil monitors can be wired to the relays, or they can also be wired externally depending upon the application that you're trying to use. The most common one is to bring it to the relays, make sure the relay gets it, and then all the alarms and the controls are being managed by the relays themselves. Then rather than making an external connection for the trip coil monitor. The most common one is bringing it to the relays.
Okay. Norman, you want to wrap up any last thought on that?
No, I agree with you, Vijay. A lot of the relays now have actual trip coil monitoring. They do a lot more than they look at they basically measure the trip coil current. They'll alert you if the duration is too long and all of that. So we do, a lot of the relays incorporate trip coil monitoring in the outputs in some of these. Okay.
Yeah, absolutely. Thank you. Panelists, thank you very much for participating and offering a lot of your insights to some of these questions. We want to thank everyone for joining, and I'll pass it back to Michael.
Eric. So as we wrap things up here, it looks like we do have a few questions that we didn't have time for here today, but we'll be working with you guys offline to follow up with you. As a reminder, a certificate of attendance, recording of the webinar, and a PowerPoint presentation with our panelists' contact info will be sent out to all attendees in 2 business days. Additionally, greatly appreciate it if you could take a couple of minutes to provide your feedback on our survey after the webinar closes, so we can continue to improve upon our future webinars and panels such as this. On the survey, there's a field where you can also request a demo or a quote on any Megger products. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars. Our next webinar is this Friday at 10 a.m. Central Time, where we will be covering on-site installation analysis for GIS using UHF and acoustic PD measurements. But with that, I'd like to thank everyone here for attending, and I hope you all have a great week.
Thank you, everyone.
Okay.
Thanks,
I want
everyone.
to thank everybody.
Thanks, everyone.
Thanks,
See
guys.
you guys. Thanks very much for the invitation. Bye.
Thank you for
Thanks,
joining.
Norman. Is it going to be posted?